Hello, this is Devam Trivedi pursuing Masters in Robotics at WPI, and I'll be presenting my project, a literature review for the project Gestura, a gesture controlled robot. This presentation covers majorly three different papers, which has a variety of methods and each defining its own methodology for controlling robots by humans, thus presenting a unique approach on human-robot interaction in its own capacity. The first paper is an EMG-based dynamic hand gesture recognition that uses Edge AI for human-robot interaction. This paper has been published by NVIDIA Labs, and the project description includes addressing the challenge of dynamic hand gestures for controlling industrial robots. Recognizing and responding hand gestures in real time enables intuitive and flexible human-robot interaction, especially in environments such as small factories. The key difficulty in accurately classifying dynamic hand gesture due to varying signals, muscle signals, and ensuring the model works universally across different users without personalized training has been the main focus of this particular paper. Over here, the proposed methodology includes having a myo armband that collects electromyographic signals or the EMG signals from the arm of a human and converts and processes using a convolutional recurrent neural network or a CRNN for classification. The model is implemented on an NVIDIA Jetson Nano to enable Edge AI capabilities, removing the need for an external computer. The CRNN combines feature extraction and time series data processing, which makes it more suitable for complex patterns of dynamic gestures. Over here, we can see at the top left, we can see a myo armband that is being worn by a human operator and performing hand gestures, which are being computed using the NVIDIA Jetson Nano, which runs the computational recurrent neural network, convolutional recurrent neural network, and comes up with a solution on how to operate and translates that into a robotic motion gestures. The robot used over here, UR3, is used by and controlled using the hand gestures such as closing or opening, thumb down, spinning, or even a fist. These motions correspond to particular motions of the robot. Over here, the evaluation of the experiments take parts in two phases, where in one phase the experimenter the data is not used to contribute to training, whereas in other the participants' data is used for training. The classifier shows high accuracy in both, that is, a classification rate of around 96.5% with participants that are familiar to the motions, and 95% for unfamiliar ones, which demonstrates its generalizability in real-time scenarios and in small factories environments. Contributions of this paper is that it provides a robust and user-independent gesture recognition model for industrial applications. This is implemented using an embedded device that highlights its potential for low latency applications in Edge AI. However, the study is limited by a single EMG sensor, which restricts the variety of muscle activities that can be captured. So, as over here, only the muscle activities that has been performed by the hand is captured using the myo sensor. Additionally, the deep learning model requires a substantial amount of data and computational resources for training, which might hinder scalability. Comparing the provided methods, we can say that CRNN was chosen for its combination of CNN as well as RNN, which makes it very effective for computing EMG signals. Comparatively, CNNs and RNNs standalone are insufficient for this task due to either limited time series capability or inadequate spatial feature extraction. However, CRNNs, which is a combination of both, is computationally intensive, and simpler models like KNNs or feed-forward neural networks might be preferable for low resource applications. However, they might have lower general accuracy. This paper also presents certain research questions, such that how these gesture recognition can be made more accurate, while that is suitable even for more constrained Edge AI environments. Can additional EMG sensors be used or other biosignals be further used that can enhance the robustness of this particular dynamic system? What are the sort of other improvements that can be made into the AI model, that is the CRNN, or develop other types of models that can process these complex gestures and provide a wider range of users without additional training? The second paper is titled Gesture Controlled Robotic Arm, published in 2023, which addresses the need for a cost effective gesture controlled robotic arm that is suitable for tasks that require precision, such as industrial applications or hazardous environments. Traditional robotic controls methods can be complex or inconvenient, especially in time sensitive or risky situations. This system uses hand gestures for intuitive control for the robotic arm, making it accessible and potentially beneficial for use in fields such as manufacturing, healthcare, and even rescue operations. The proposed methodology involves having a robotic arm that is controlled via sensors adapted on a glove. An Arduino Mega microcontroller is utilized to receive data from the flex sensor and a gyroscope that is mounted upon a glove that is worn by the user. This flex sensor controls the wrist and claw of the arm, while the gyroscope directs and the base of the forearm. Based on the glove's orientation and finger bending, the sensors translate hand movements such as up or down or turning left or right into servo motor rotations that allows precision control for the robotic arm. We can see over here how the setup for the methodology takes place. That is, we have an Arduino Atmega controller which is at the heart of the setup, that is controlled using two flex sensors and is connected to multiple servo motors which are attached to the claw of the robot. We can see over here how the four parameters, that is the X and Y axes, along with the claw positions and the wrist positions, are taken into consideration and computed by the Arduino Mega controller, and that translates into the 4 degree of freedom for a robot that can control the claw as well as the wrist of the robot. The evaluation experiment for this paper includes that each sensor's functionality showing how they control different parts of the arm. For example, the claw opens and closes based on the flex sensor input from the glove's index finger. The paper also provides measurements and angles on rotations for each joint and highlights a 1 second latency between gestures and arm movements that is being shown in the robot. This paper highly contributes to showing how Arduino Mega is an affordable and intuitive way to control a basic robotic arm. It also uses a glove-based input that makes it more adaptable for different appliances and facilitates the use of more complex interfaces. However, this method too comes with its own limitations, such as having a 1 second latency, as has been explained before, that could severely impact performance in certain real-time applications. Additionally, the glove needs to be physically connected to the robotic arm, which limits its mobility and range. The system lacks object recognition and adaptive grip, which could hinder more advanced manipulation tasks. This paper has pros such as the system is cost effective and simpler to implement as it uses only a flex sensor and an Arduino Atmega processor, thus negating the use of networking protocols such as Zigbee or more complex sensor, which makes it accessible for suitable for small scale applications. However, since it uses an Arduino, it does not have many other functionalities that other high-end microcontrollers or wireless modules have, such as having greater flexibility, having faster response time, having low latency, as well as having an enhanced range. This paper produces research questions such as how can latency be minimized in a gesture-controlled robotic system that enhances real-time responsiveness. What are the certain improvements that could be made to take the entire system on a wireless level and enable the wireless communication between the glove and the robotic arm? Can there be object recognition and adaptive gripping functionalities be incorporated into the system that may expand the system's manipulation task capabilities? How might machine learning algorithms that can be integrated into the microcontroller improve the gesture recognition accuracy for different types of users? Coming to our last paper, we have hand gesture recognition and voice controlled robot. This paper addresses the need for intuitive robot control that can assist people with physical disabilities. Traditional robots are controlled manually, which can be challenging for individuals with mobility or communication limitations. This paper proposes a solution that combines hand recognition and also voice recognition to control the robot, which makes it further more easier for people who may be unable to use standard control methods to operate the robots independently. The proposed system uses a combination of an MPU 6050 sensor for gesture recognition and a Bluetooth-enabled smartphone for voice control. The MPU 6050 sensor captures hand gestures including forward, backward, left and right and stop commands, which are interpreted by an Arduino microcontroller. The voice commands are processed via a mobile application that converts spoken commands into text and sends them to the robot via Bluetooth technology that allows the user to control the robots by either of the two methods. Over here we can see on the top left we can see the flex sensor in action, where the hand motion can be interpreted by the flex sensor as backward or forward motion into the robot. On the right side we can see how an Arduino is used and an LCD along with a Bluetooth controller, as can be seen in the bottom left corner, which can translate the text messages from the camera from the mobile phone to the robot and can be displayed on this LED screen that has been mounted atop the robot. The evaluation of the system includes testing of each gesture and voice command to ensure accurate responses from the robot. For gestures, the robot moves in the simplified directions based on the orientation of the MPO6050 flex sensor. For voice control, commands like front, back, left, right, or even stop, all these commands are used, and the system displays the command on an LCD that confirms the successful reception and execution of the particular command that is being sent by the human via voice controlled via the smartphone to the robot. This paper provides a dual mode control system for robotic operation, which is not done by many other papers, which enhances accessibility for users with disabilities. It also combines the simplicity of Bluetooth with Arduino for straightforward communication and control, thus providing a cheaper, low latency method for controlling a robot. This, however, poses the limitation as by using a Bluetooth technology, we restrict the range and the connectivity that may be present between the operator and the robot. The voice control feature depends on smartphone compatibility, which could limit the accessibility for users without specific mobile devices or applications available to them. This paper provides accessibility for a broader range of users and can be adapted for various applications from industrial as well as personal assistance. However, the gesture-based control is sensitive to hand positioning, which might lead to errors since the flex sensors are not 100% accurate, and Bluetooth definitely limits the system's operational range that makes it less suitable for large-scale applications. Certain research questions can be posed in this system, in this particular project, that is, how can the system be adapted to work with other connectivity options to expand the operational range? Can machine learning be integrated to improve gesture recognition that can improve accuracy for various hand orientations and speeds other than just forward or backward? What are the other improvements that may be necessary to make the system more compatible with different mobile systems or even operating systems or other appliances? The last research question that it poses is, how might this system be expanded to recognize more complex gestures or additional voice commands for multifunctional control of the robot? Thank you.